Hello, my name is Narayanan, and today I'm going to be talking to you about this study, Managing Uncertain Tasks in Technology-Intensive Project Environments, a multi-method study of task closure and capacity management decisions. This is joint work with Balasubramanian and Swaminathan and Zhang at Clemson University. We are indeed honored to be a finalist in the Jack Meredith Award of the Journal of Operations Management. I'll briefly touch upon the introduction and problem motivation, talk about the empirically grounded analytical model that we worked on in this study, and the simulation model, and talk about the implications. The motivation for this study came from task resolution challenges in a software firm where engineers were solving on software bugs. And the challenge was that customer was very unhappy with high average time for resolution, and engineers typically worked longer than what they thought they should need. And all the incoming tasks were typically treated alike, and managers frequently suffered from resource allocation challenges because they were wondering how they could help the engineers figure out allocation of their bandwidth appropriately. And this is also common in other settings. For example, there is a study in HBR by Roger Bond on firefighting, and Nelson Repenning has also talked about firefighting in the new product development space, where they have used system dynamics models to study them. So there are other real-world connections into the project management environments where there is significant uncertainty in many project management environments, such as software development and maintenance, engineering change order resolutions, go, no-go decisions. All of these are characterized by uncertain tasks. And it turns out that economically, this issue is also pretty significant because more than 50% of the bugs budgets in software is dedicated to maintenance activities, and that's quite substantial. And ECOs, engineering change orders, also comprise of 20 to 50% of product costs, and many of them have uncertain resolution times. This also has relationship to the escalation of commitment literature in project management. So the study, our study primarily focuses on resource allocation and management of productivity through better process management and using the traits of the process for managing the resource allocation efforts. So we use about 4,335 debugging tasks performed on a very large system software with more than 1 million lines of code on a subsample of about 4 teams from our data set. So there are about 24% of the tasks in our setting that was closed with no resolution or workarounds, where engineers would actually suggest workarounds, but they cannot fix the task, but they would have spent a substantial amount of effort before they would have closed the task. So essentially, our idea was, why not think about putting together mechanisms in place where these 24% get more visibility, and we sort of also talk about the bandwidth allocation of engineers on these 24% of the tasks. To do this, essentially, we took a 3-part approach. We first solved an empirical model, then we looked at an analytical model, and then we used a simulation model where the parameters for the simulation came from the analytical model. And I'll share how the simulation was helpful. So step 1, the empirical model, we primarily used a beta geometric hazard distribution that we estimated. In this picture, you would find that the model fits very closely to the long tail problem. What this figure shows is that when a task tends to stay in the system, the successful resolution probability for the task substantially drops. If the successful resolution probability substantially drops, then engineers tend to work on the task more and more, and perhaps are going to be closing them. So we use this basic insight from the beta geometric model to work out a very simple analytical formulation drawing from Kaplan et al. 1992. And what we focus on there is, could the system performance be improved by imposing a limit on the effort? And what are the trade-offs? So just to reiterate, the idea here is, when engineers are working on tasks, which we call as bugs in this picture, or bugs or maintenance tasks, either one of them, MTs. When these tasks come into the system, they try to take a shot at working on the task. If it does not work, they keep taking multiple iterative shots on these jobs so they could resolve them. But what happens is, as the tasks stay in the system longer, the less likely they are to be successfully resolved. The findings from the analytical model basically reinforce the idea that the resolution probably flattened out as time went on. What we did was, once we solved the basic formulation and estimated out the parameters for our survival function, we used these parameters in a simulation model, which was to take it closer to the real world, because in the real world, the engineers are working on multiple priority classes, they also preempted. So if a high priority job came in, they stopped everything else and worked on the high priority job before they would move down to the lower priority job. And they also pooled tasks. Engineers could have multiple tasks open against them. So we tried to take it as close to real world as possible by accommodating all of these in a ground up simulation that we designed using C++. And the core insights are pretty interesting, where what we show is that in about 1/6 of the maximum time these bugs tend to last in the system, I would say, sorry, not 1/6, but about 17% of the time, it's about 52 days out of 300, in about 72% of the time of effort allocation, you lose only about 5% of the successful resolution rates overall. When your capacity is only 67%. This has to be seen in the light of the fact that there is a lot of turnover in these environments where engineers tend to quit these jobs in random, which puts a lot of pressure on management to be able to reallocate bandwidth. So essentially what we were suggesting was that you could actually explore options where you could impose closure policies, or rather at least openly consider closure policies, and allow engineers to be forthcoming with these alternatives if they can find a workaround. So essentially, the idea here is that there's a substantial resource benefit for such closure policies. When we actually think about pooling, our results are really interesting, because what we find is that a pool of 2 tasks for an engineer gains the best trade-offs in terms of throughput increase, which is about 42% compared to the baseline, and successful resolution rates, you only lose about 5.7%. And service time reduction is about 7.68%. So essentially what we are saying is that our simulation suggested that in very constrained capacity scenarios, when engineers are managing multiple priority classes and task pooling, a smaller pool works really well from an overall trade-off standpoint. That's the core insight result of this part of the simulation. So our implications for this study, it has multiple implications. One is certainly it provides a framework to understand uncertainty in task resolutions and managing firefighting efforts. We also, in the paper, talk about using scenario planning, such ideas for scenario planning, particularly in our context in offshore settings. Managers frequently struggled with overtime allocations when task queues piled up. So they could always work with the client and show data and show how capacity constraints can be driven by the nature of the task itself. And we show that limited pooling results in substantial benefits. There's a paper by Jordan et al. Which focuses on cross-chaining, and it has implications with respect to that. And we also show formal approaches to handling escalation of commitments in projects. Thank you for the opportunity to present, and the citation for the paper is below. We truly appreciate this opportunity.